A way to quantify our process capability and where it's sitting is to take a look at what's called the process capability ratio. And it's defined to be the upper specification limit minus the lower specification limit divided by 6 sigma. Right? And that 6 sigma is coming from the perspective that if we looked at mu plus or minus 3 sigma, the band or the width that we would end up with would be 6 sigma. And that 3 sigma is coming from sort of a natural tolerance limits where, and again that's sort of that plus or minus 3 sigma to give us a total of 6 sigma, and that's widths. And we choose that because in that normal distribution we end up with that 99.7% of the population is between the plus or minus 3 sigma level, hence this 6 sigma approach. Right? And if you were to take a reciprocal of this and express it as a percentage, it would say something about what fraction of 6 sigma is, what fraction 99.7% is compared to the width provided by our upper specification limit and our lower specification limit. So let's take a look at a couple of different kind of scenarios here where we've got different normal distributions, meaning different standard deviations plotted with the same upper and lower specification limit. Now, one other aspect here I want to point out is that how do you establish these upper and lower specification limits? And if you don't have standards setting organizations that are setting these, now let's say you're sort of in fresh virgin territory where pure engineering and you got to balance things, and let's not make this a severe risk kind of situation where if you don't quite meet the specification limit there's a fatality or some serious injury. Let's stay away from that kind of scenario and just say where might you generally come up with something like an upper and lower specification limit. They have everything to do with the limits that you've set on the, for instance, the functionality of the particular part. And so that comes from design considerations, translating the design criteria and how you're maybe assembling things together. And these are not, let's make this absolutely crystal clear, these are not the same thing as control limits. They bear no relationship at all to control limits. Okay, so here we have our process distribution here, and here are 2 particular limits. And for now we're going to assume that our mean is centered on the 2 limits, so that the mean is basically the average of those 2 in this initial kind of view. And when we do that, and you'll note in this first one here that the 3 sigma range for the distribution we have a shown, I've carefully crafted it so that it's exactly equal to one of these tick marks that we see here. And so it's quite a bit smaller than what this is here. So we're quite a bit tighter in our process control. This is going to be smaller, a total of 6 sigma than that. So our PCR is going to be greater than 1. Right? And then if you look at this one down here on the other hand, the 3 sigma range actually turns out to be all the way out to our specification limits. So this has a wider standard deviation associated with it in lower height, so that total area under the curve is 1, right? I know it doesn't quite look like that. I did some additional scaling as I transported it over from my graphing package over to the Word document. So I lost the total actual scaled area there, but it's supposed to represent that. And note that in that case, our area that is sitting out in the tails is going to be 0.0027 divided by 2, right? Equal area in each tail, total area being that 0.0027. That this is a PCR of exactly 1 for this case compared to our other case. And then finally our last one here, we have an even larger spread, and our 3 sigma goes out even further, and our PCR here is less than 1. And it indicates that our process capability, our variability that's going on is much broader, and we're extending out past our specification limits at a much higher fraction of time. So here our area is going to be greater than 0.00127 over 2. And note, these areas outside are essentially our non-conforming units. So deciding what our desirable PCR has a little bit to do with perhaps deciding what our tolerance level is, what our acceptability rate is for being outside of that. And we'll have an example problem that will talk about that in just a little bit. Okay. Now, another part of this here is that we don't usually know our standard deviation in our real situations. Instead, we're estimating it through one of 2 approaches, and this is similar to what we talked about in the control charts, in terms of we could estimate it based upon the average range that we're getting out of our sample, and then divided by D2, same statistic as or constant as before. Or we might do it with instead our sample standard deviation, and then that will be divided by that constant C-force. So either approach that we might go after there is acceptable in our overall approach. I think we're still recording. I'm going to proceed as though I think we're still recording and hope that we are. Great. All right, so another potential situation is that our mean is not equal to the average of the upper and the lower specification range, and our process is shifted to one side or the other. Right, in that case, then how do we handle the PCR? And so if mu is not centered here at that location, is shifted to the left in this particular one, what we're going to do is we're going to pretend as though we're going to make an equivalent kind of scenario here. So here's our center, and there's our 3 sigma bound. And we'll calculate our PCR based upon which one we're closest to. And so if it's closer to the lower limit, that would be mu minus our lower specification. And now we're going to divide by 3 sigma. So before this was USL minus LSL all divided by 6 sigma. Here now we're just going to shift over our numerator by this distance here. Right, and then so we're going to be comparing that distance to this one. And if we were, of course, at the other side, it would be our USL minus mu divided by 3 sigma. Now we don't really have to calculate both of those, but if you were putting this into a spreadsheet and wanted to cover all kinds of possibilities, then you could then just take the min of those, calculate both, take the min of either one. Only one of them is really significant to you. It's the one that you're closest to. and we call that the PCR sub k for that particular situation. So let's take a look at a numerical example, and I'm going to choose to do one that's directly out of your text. I don't always like to do that, but there's a numerical mistake that's in the text. It's not a significant one in terms of the final results, but if you're studying that, trying to understand what they're doing, and you see an intermediate result that doesn't make a lot of sense, then potentially the reason why is because they made a really just a typographical mistake there. And so this is an electrical circuit where the specifications are through this one particular area that the current should be in the range of 100 plus or minus 10 milliamps. And they've taken a look at the process mean and standard deviation, and they have 107 milliamps for the mu and sigma of 1.5. Now, they're presuming here that they actually know the entire population value of what's going on in the process as opposed to a sample here. So keep that in mind as we're processing some of this work. So they want to know what is the PCR and the actual capability, and then what is the probability that the process is out of specification. Right? And so the PCR is again just purely and directly the upper specification limit minus the lower specification divided by 6 sigma. And our upper minus our lower is really just twice or plus or minus, right? So you could write this as 110 minus 90 if you want, but it's really just 2 times the 10. And then over 6, and here's where they made their mistake, they wrote a 5 down instead of a 1.5. Right? And so the number that they calculate turns out to be correct. That's 2.22. 20 divided by 9. And I'm going to do it on my calculator again real quick. You bet that really is right. Right, so that PCR is correct. Now, notice the mean is shifted over, right? It's not, the mean would be 100, and so the PCRK, the actual capability, that's what this really is, then is going to be, well, we're close, we don't have to, again, don't have to calculate both of them. We know we're closer to the upper, so we'll do USL over mu divided by 3 sigma. And so our upper is 110 minus the 107, and then divided by 3, and again, here's where they made a different error. I think they put 15, it should have been 1.5. And of course, now we have 3 divided by 3 all over 1/2, and so that's really just 2/3 or 0.67. So the number, again, is correct that they show, it's just that the intermediate stuff right there and there is where they made a typographical mistake. Okay. Now they also go on to calculate what the probability is that the process is out of specification. And they look at both the upper limit and the lower limit. And this is just a straightforward normal distribution calculation. What's the probability here? Excuse me, that x is less than our lower specification limit. Right? And so with us knowing these specific population parameters, then it is directly a normal distribution calculation. So we can go straight to that z is less than, and we'll have then, see, lower specification limit, so that's 90 minus our mean of 107 divided by our standard deviation of 1.5, and that'll turn out to be minus 11.3, and which is way out there, and our cumulative function there is equal to 0 on that one. For the upper one, so in other words, we have very little chance of ever being lower than the lower specification. For the upper one, then that's going to be 1 minus the CDF, of Z being less than the USL minus our mean divided by sigma. Right? So I did a little flipperoo deal here, and so that's 110 minus 107 divided by 1.5. So that's 3 divided by 1.5, or of course 2, and the probability that this 1 minus that is going to be 0.023. Right, so there's about a 2% chance that our current is going to be larger than our upper specification limit. So total aggregate out of spec probability is, you add the 2, of course 1 is essentially 0, so you end up with approximately 2% chance. And you have to decide whether that's acceptable or not, which is not a part of the numerical part of the problem, but it is, from a big picture practical standpoint, you have to decide what your likelihood is, and that is not just a decision associated with looking at numbers, but it's you also have to take into account business decisions as well as the engineering consequence of, okay, what if this is larger? Right, what happens engineering wise? Right, so and what else could you do? Well, one of the things you could do is actually take a look at, is there a way to reduce this mean shift? It's not really maybe so much the spread that's at issue, it's the mean is shifted pretty far away from 7% away from that. So maybe that's a big deal, and maybe that's not too hard to shift over. You can get it down to 105, then that becomes 5 divided by 1.5, and this number starts to fall off maybe pretty quickly or quickly enough. Okay, and one last then aspect of this whole PCRK business is that we often, what we end up doing in production is we often are desire to keep our PCR sub k greater than 1.33. Okay, and for situations that are a little bit more critical, or items that might be related to strength or safety kinds of issues, then it's common to have PCR sub k greater than 1.66. And even at the instance that you get it up to 2.0, then you have the special case of what we call having achieved the 6 sigma process. That our process mean is going to end up, it turns out, with this ratio, the process mean is going to turn out to be 6 sigma away from the specification limits on either side. And that's a fairly significant kind of situation. It tells you that the likelihood that you're outside of the specification limits is exceptionally small. Right? A PCR of 1 tells us that we're only have a chance of about 0.27%. And double that now to 6 sigma away. Right, before the other one was only 3 sigma away. The mean was only 3 sigma away. Now we're going to go 6 sigma away, and that's going to be an exceptionally small likelihood, and is in some ways a measure of quality.